Alright, in this next lesson we're looking at radiation, so this is just the properties. Right, so the types of radiation, three types of radiation we are interested in, and the properties we're going to look at are alpha, that's the symbol, beta, and that's the symbol, and gamma, and that's the symbol. Alright, alpha, beta and gamma, and they were discovered using cloud chambers, and they then knew that they did different things, they behaved differently, so there must be different particles, let's call them alpha, beta and gamma. So that's what they did. Then later on, of course, some things were found out about them. So our alpha particle was found to be a particle. So its properties is that, in fact, it's a helium nucleus. Which is 4,2He, and it's got a 2+ charge. Now, when we say it's a helium nucleus, it's made of 2 protons and 2 neutrons, which is what's in a helium nucleus. But the thing that's different is that it's from a decayed nucleus. Right, so the nucleus that's decaying of that radioactive element shoots that out of it. So it's got a charge because it's not balanced. The protons are not balanced, so it's got 2+. So then it's 4 atomic mass units. And 1 atomic mass unit is mass of a proton, so it's 4 times the mass of a proton. Now it's penetration, and you would have seen that in the videos that I've got there, the radioactive isotopes, alpha, beta, gamma, demonstrated, and an explanation of them. So you would have seen penetration is a few centimetres in air, so it doesn't go very far in air at all, and paper. So these next two things ionise easily ionises atoms, and these two things here, they're connected with each other. Alright, so if it's ionising atoms, it's banging into their electrons and knocking them out. And if it's banging into electrons and knocking them out, then it's losing some of its momentum, its kinetic energy, and so, it stops, so it gets absorbed a few centimetres in air. And in relative terms to the others, it's slow. So, when we say it's slow, it's only 10% the speed of light. Right, so that's pretty slow. And we've got small deflection in magnetic and electric fields. Alright, small deflection because of its mass, so relatively speaking, 4 atomic mass units relatively heavy in terms of that. Alright, so that's how an alpha particle behaves. The next one is our beta particle. There's actually two types of beta particle. So there's an electron and a positron. So they come from the nucleus. So you kind of think, well, how does that work? So it depends on what decays in the nucleus. So the electron, which sometimes we call that a beta minus, we get an electron when a neutron decays. So we get a proton plus an electron, and then that electron shot out, and that's our beta minus particle. Our positron, beta plus, we get that when a proton decays. So if a proton decays, we end up with a neutron plus our positron, and our positron is shot out. Alright, so two types of beta particles. Most commonly we think of the electron, the beta minus, but there are two. Alright, so the charge, of course, is negative charge on an electron if it's a beta minus charge on a proton. Now the mass of these things in comparison to an alpha, 1/7000th, so tiny in comparison. Now to absorb penetration, because they're smaller and lighter, they go a few metres in air. And lead, as it says, 3.5 centimetres. So they're weak at ionising. Ability. And as I said before, these two things are connected. So if they're small and light, small things, light, don't bang so easily into electrons. And so they don't bang the electrons out of the place, so don't ionise, and because they hold their kinetic energy, they go further. Now, in comparison, these are pretty fast, these ones. Right, they're fast. They're about 90% of the speed of light. Alright, and large deflection, because they're light. That's to do with the deflections, to do with this more so than the charge. So we've got large deflection in electric and magnetic fields. Alright, so that's our beta particle, that's its properties, and that's all we're looking at the moment in this particular lesson. We're just looking at what the properties of these things are. Alright, now the next one is actually not a particle. So it's a gamma, and it's called a gamma ray. Now why do we call it a ray? Well, because it's part of the electromagnetic spectrum. So it's an electromagnetic wave. So it's not a particle at all. Alright, so it's electromagnetic radiation and has no charge as such, has no mass. So it's not going to change that. Penetration in steel, it's about 30 centimetres. It's about 30 centimetres in steel. So a lot, and in air doesn't ever really get absorbed. So they're very weak ionising. Alright, so if they've got a huge penetration, they're not banging into stuff, so they're not going to ionise. And because they're a wave, got no charge, no deflection. In electric and magnetic fields. Alright, so the lethal effect on tissues. Which is quite handy in that you can use them to treat cancer stuff. Alright, so even though they're weak ionisation, they still have lethal effect on the tissues as they affect the nucleus of the cells. Alright, and so with all of these, as well as these, the thing that all of these have in common is that they're coming from the nucleus. Alright, so all these three radiations come from the nucleus. Alright, now there's energy involved with these things, and it's a really, really small amount of energy in terms of what we understand. So scientists speak in terms of this thing called electron-volt. So that's the energy that you would get from one electron accelerating it by 1 volt. And 1 electron-volt is 1.6 by 10 to the minus 19 joule. Alright, and so the numbers of electron volts we talk about, when we talk about joules, it's very, very small. So the electron volt is generally determines the energy that we use. So 1 electron accelerated by 1 volt is 1 electron volt. Alright, here's an example, and that's it, just some, as I said, just some properties of the different radiations, then a definition of the energy, and so here's an example about what we might do with the energy. Alright, so uranium-238, that's something very commonly we know emits, and it emits alpha particles, so it emits alpha particles, and maximum energy of that, 4.2 mega electron volts. So mega, just a reminder, is 10 to the power of 6. So explain why a sample with this radioisotope encased in plastic is quite safe to handle, yet even inhaled as dust would be considered dangerous. Alright, so why alpha particles? Alpha particles, that's got to do with penetration. So when we go back to our alpha particles all the way back here, whoops, there we go, gone too far. Penetration, a few centimetres in the air, so they don't penetrate very far. So, a few centimetres in the air, so the plastic will absorb. So, they're not going to get into your body somehow or other, and then cause problems. However, the dust, so if it's in the air, gets into the lungs, So then it's going to affect your lung tissue. So the lung tissue is exposed, and so the lung tissue would absorb the alpha particles, which then you have a risk of some sort of radiation poisoning. Alright, so the question part B says calculate the energy of an alpha particle in joules. So this is the conversion. So 1 electron volt is 1.6 by 10 to the minus 19 joules. So when we've got 4.2 by 10 to the 6 per mega electron volts, if we want to do that into joules, we multiply by 1.6 by 10 to the minus 19. And when you do that on your calculator, you get 6.72 by 10 to the minus 13 joule, which is quite a small amount of energy. So as you can see, 4.2 mega electron volts is far better to be talking in those terms as far as scientists are concerned. Rolls off the tongue a lot easier than 6.72 by 10 to the minus 13 joule. So that's why they use that. Alright, up to problem set number 5 now. So there's some questions in the book about that. Don't forget, watch those videos, they're quite informative. And any things in the red that's missing that you have missed, don't forget the notes are on the website to look at that too.